Imagine for a moment that the human story doesn't stop at the beach, the plains, the cities, or even the planets. Imagine it keeps going, one step at a time, out past our moon, past Mars, out of the solar system entirely, and then across the stars. What would that journey actually look like if we tried to spread civilization across the entire Milky Way? It helps to break it down into a sequence of practical steps and technological milestones, because taking on the galaxy isn't a single leap. It's a chain of smaller, concrete actions building on each other. Step 1 is the obvious first step: turn Earth into a reliable launch pad. Right now we send things into orbit with chemical rockets and rely on Earth for almost everything: materials, food, spare parts, the manufacturing base. Before we can sustainably expand into space, we need an off-world economy. That means regular, low-cost access to orbit, big manufacturing plants in space, and a flow of materials that doesn't depend on hauling everything up Earth's gravity well. Think of it like developing a port city with docks, warehouses, and factories. Once the port works, ships don't have to keep returning to the mainland for everything. Practically, that involves a few technologies: reusable launch vehicles, better spaceplanes, and eventually fully reusable second stages or space tugs. It also means mining local resources where they are easier to extract. The Moon, near-Earth asteroids, and the moons of the outer planets are all full of rock, metals, and ices, raw materials that we can turn into fuel, building materials, and life support. Extracting water from lunar polar ice or from hydrated minerals on asteroids is a huge game changer, because water can give you breathable oxygen, rocket propellant, hydrogen and oxygen, and radiation shielding. Step 2 is establishing reliable settlements inside the solar system, bases on the Moon and Mars, and large orbital habitats. Consider the Moon as a first workshop. It's nearby, it's low gravity, it has regolith full of useful elements, and it has permanently shadowed regions that trap ice. A lunar base could operate as a shipyard. Use local metals and solar energy to build habitats, glass, and solar arrays. Mars is a next step, a planet with day-night cycles similar to Earth and resources more varied than the Moon's. But both the Moon and Mars are harsh places. So alongside surface settlements, we should think in terms of orbital habitats, big rotating stations that simulate gravity, built from materials mined in space. These are like city ships that can be positioned where they're most useful: near a planet, deep in space, or in orbit around a distant star later on. To make these habitats work, we need closed-loop life support systems, ways to recycle air, water, and nutrients with very high efficiency, and industrial automation that can keep factories running without hundreds of thousands of human workers. We'll need robots that can handle construction in vacuum and dust, sophisticated 3D printers for metal and ceramic parts, and AI systems to coordinate complex manufacturing processes across many sites. Step 3 is learning to use local resources everywhere we go, in situ resource utilization, or ISRU. The economic and energy cost of hauling everything from Earth is prohibitive. But any asteroid, comet, or moon you find will have metals, silicates, and often water ice. If you can mine it, process it, and use it to build habitats, fuel, and tools, you are no longer bound by Earth's supply limits. Imagine automated factories landing on an asteroid, digging out ores, smelting iron, and printing pieces of a habitat, all with machines that can copy themselves to a degree. That's the core idea behind getting off Earth in a sustainable way. Step 4 is propulsion. For travel within the solar system, chemical rockets do a lot of work, but they're inefficient for interstellar distances. To travel between stars, we need fundamentally different engines. Several concepts exist at various levels of maturity. Nuclear thermal rockets, which heat a propellant with a nuclear reactor, offer better efficiency than chemical rockets. Nuclear pulse propulsion, a once serious idea called Project Orion, uses small nuclear explosions to push a craft and could give enormous thrust. Fusion rockets, using fusion reactions like the ones that power the sun, promise even better performance, with designs such as Project Daedalus explored on paper. Laser-driven light sails are a very different idea. Instead of carrying fuel, a craft has a reflective sail and gets pushed by a powerful ground or space-based laser beam. Breakthrough Starshot is a current project that aims to send gram-scale probes to nearby stars at perhaps 20% of light speed using a laser array. Each propulsion method trades off payload mass, speed, and technical difficulty. With propulsion options in mind, Step 5 is sending robotic scouts and seed ships. These are our first interstellar travelers. They're not huge colony ships carrying thousands of people. They're robotic explorers designed to survive long journeys and, crucially, to make use of what they find. One especially powerful idea is a self-replicating probe, sometimes called a von Neumann probe. The basic idea: send a probe that can land on a resource-rich body, build factories using local materials, produce copies of itself, and then send those copies to other systems. It's like a seed that germinates into a tree that drops more seeds. If this works, colonization could expand exponentially, because every new outpost can build more outposts. The engineering challenge is enormous: mining, refining, manufacturing, and sophisticated robotics all in a remote environment. But the payoff is that you don't need to carry all the material and people with you. There are also seed factories that don't try to reproduce full probes immediately. Instead, they build local infrastructure, power plants, smelters, 3D printers, and habitats. Over decades or centuries, they scale up a site so that it becomes fully self-sustaining. When a seed factory is mature, it can support human settlers or manufacture more probes to expand further. This bootstrapping approach reduces the immediate complexity of each probe. How long would this take? The scale is huge. The Milky Way is about 100,000 light-years across and has something like 400 billion stars. Even if you travel at a significant fraction of light speed, crossing the galaxy takes enormous time. But colonization is a branching process rather than a single ship going edge to edge. If you can reach the nearest star in a few decades or a few centuries and build a factory there that then sends 2 more missions, and those 2 send 4, you get exponential growth. Simple math suggests that even fairly slow expansion can fill the galaxy in a time short compared to geological timescales, perhaps a few million to a few 100 million years, depending on speeds and replication times. That's long compared to human history, but short compared to the age of the galaxy. The key takeaway isn't that it's immediate, it's that the galaxy is traversable in principle if you are patient and methodical. Step 6 is creating habitats adapted to each new environment. Many exoplanets may be too cold, too hot, too irradiated, or locked tidally to ever be comfortable for humans without massive change. Terraforming, altering a planet's atmosphere, temperature, or magnetic environment, is sometimes discussed, but it's slow and expensive. A more practical approach is building orbital or surface habitats that don't require changing a planet's entire ecosystem. Imagine huge bubble-like cylinders, rotating to simulate gravity, built in orbit and supplied with materials from nearby asteroids. These O'Neill cylinders, named for the physicist Gerard O'Neill, could hold millions of people and be tailored for different climates. They can be located around many types of stars, and you can pair them with mirrors or sunshades to manage temperature. If a planet is welcoming, good. If it's hostile, you build a habitat that bypasses the problem. When settlers do go to actual planets, they'll likely adapt. Humans have always adapted with technology and social structures. On Mars, for example, pressure domes, subsurface habitats, and greenhouses would allow agriculture and normal human activity with lower energy cost than trying to make the whole planet Earth-like. For distant systems, we would probably send a mixture of automated infrastructure first and human settlers, only when a dependable supply chain or fully autonomous life support exists. Step 7 is the transfer of culture, skills, and governance. You can build habitats and factories, but you also need systems for law, trade, knowledge preservation, education, and conflict resolution. Communication across interstellar distances is slow. Even to the nearest star, messages take years. That means colonies must be highly autonomous and able to make decisions on their own. A straightforward hierarchical empire model won't work the way it did on Earth when messages took weeks or months. Over light years of distance, central control is impossible. Expect a patchwork of semi-independent societies with shared roots but diverging laws and cultures. Economically, many things that are rare on Earth will be abundant in space: metals, certain volatiles, and vice versa. The incentives that drive settlers will differ. Scientific curiosity, resource opportunity, religious or ideological motives, the desire for new social orders, or simply the urge to survive. Step 8 is scaling up energy use and building megastructures. A small colony can run on solar panels and local fuels, but to truly expand across many systems, you'll need much more energy. One idea that reappears in many discussions is the Dyson swarm. Instead of a single perfect shell around a star, build a vast cloud of solar collectors and habitats that intercept a large fraction of a star's light, converting it into usable energy. With stellar-scale energy, you can do large-scale manufacturing, move large masses, and support huge populations. Dyson swarms are built piece by piece, send robotic factories to harvest asteroids, and create millions of satellites that orbit and harvest energy. Over centuries that could produce extraordinary amounts of power. Step 9 involves solving practical problems of interstellar travel itself: radiation, micrometeoroid impacts, and the need for shielding. When you're moving at a significant fraction of the speed of light, even tiny dust grains carry enormous kinetic energy and can punch holes through a hull. Solutions range from physical shielding, layers of water, ice, or packed regolith, to magnetic or plasma shields that deflect charged particles. For small, fast probes like laser sails, shielding is lighter because they're small and inexpensive. You can send thousands and accept that many won't make it. For large human ships, you need mass, redundancy, and repair capabilities. Another technique is to accelerate slowly and keep speeds moderate, reducing the damage risk, but that increases travel time. Step 10 is the choice between biological and non-biological expansion. Sending humans is hard. You need life support, supplies, protection from radiation, and long-term social coherence. An alternative is to send uploading-capable machines or AI-based settlers. Digital minds can be stored compactly, survive harsh environments, be copied, and operate at fast subjective speeds. They could run automated factories that build habitats optimized for their needs. If you could reliably copy minds and run them in silicon habitats, colonization becomes much cheaper in mass and energy. But that brings philosophical and ethical questions. Do you keep humans at the center of expansion, or do you send AI vanguards? A mixed strategy is plausible. Send robots and AI to prepare a site, then humans follow once it's stable. Step 11 is the ecology of expansion. How do you avoid destroying local ecosystems or accidentally wiping out alien life? If we find a truly living world, we face a dilemma. Do we colonize and risk extinguishing its biosphere, or do we protect it and limit our expansion? Responsible expansion means strict planetary protection when life is possible, careful study, and perhaps prioritizing non-biological habitats or worlds that are sterile. There's also the flip side. If we seed life, intentionally or accidentally, we become agents that change biology at a galactic scale. That's a huge responsibility. Any realistic expansion plan should include protocols for detecting life and rules for how to proceed. Step 12 is the manufacturing chain out to the stars. Think of each new star system as a node. To colonize from one node to many, you need supply chains that reach across light years. But unlike in the early days of Earth's colonization, you can build factories upon arrival that are largely autonomous. Early probes might be heavy and carry the key high-tech blueprints and the most delicate components, but later generations will be constructed from local metals and ice, using local electronics manufacturing, 3D printing, and nanotechnology. Advances in materials science and nanofabrication could allow tiny machines to assemble larger structures atom by atom or molecule by molecule, turning raw ore into chips, sensors, and components. Robotic assembly lines could be entirely self-contained, drawing power from stellar collectors. Step 13 is about the economy. How do you make expansion pay for itself? On Earth, colonization often followed commercial motives: resources, trade routes, or new markets. In space, raw materials are abundant in many forms. What's scarce is concentrated megastructures and habitable environments. Early economic incentives may come from resources that are rare on Earth, for example, platinum group metals or helium-3 useful for fusion. Over time, the economy shifts to energy capture and manufacturing at scale. If you can produce things in space far more cheaply, because of microgravity and access to raw materials, you can export manufactured goods back to Earth or trade among colonies. Trade can also be in knowledge, biotech, or cultural products. Step 14 is the sociology of long-term settlements. Human societies are complex and often unpredictable. Over generations separated by light years, cultures will diverge. Languages will change. Political systems will evolve. Some colonies may prefer strict order, others extreme freedom. Some may prioritize exploration and science, others the accumulation of wealth. These social differences can be a strength. Diversity increases the chance that some groups will adapt to new environments, but they can also cause conflict. Mechanisms for diplomacy, conflict resolution, and shared norms will be necessary to keep cooperation viable across those distances. Religious and ethical views on colonization, contact with other life, and the rights of AI or uploaded minds will shape politics. Step 15 is redundancy and resilience. At interstellar scales, accidents happen, systems fail, civilizations rise and fall. To guard against existential loss, we need redundancy in the form of many independent colonies and repositories of knowledge and genetic information. Think of seed vaults and libraries spread across space, with multiple copies of human culture and biology stored in different systems. If one colony collapses due to internal strife, a local catastrophe, or a technical failure, others survive. This strategy is already sensible on Earth. At galactic scale, it's essential. Step 16 is the role of communication and knowledge transmission. Even if colonies are politically independent, they can still trade information. A colony with a new manufacturing technique can send the blueprints to others, taking perhaps decades to arrive. Over centuries, technologies can spread much faster than people can travel. Beacons and relay stations could help facilitate communication, but they can never overcome the light speed limit. So systems will develop both a local tradition and a shared knowledge base, updated over centuries. Step 17 is the trade-off between speed and cargo. Fast ships like laser-sailed probes are lightweight and cheap per trip, but can't carry many people or heavy equipment. Slow ships can haul much more but tie up resources for centuries. This trade-off shapes strategy. Use fast probes for scouts and information, and use slower, heavier ships or staged missions to build the infrastructure needed for human colonization. Over time, as local production matures, the need to haul heavy items across interstellar space declines. Step 18 is addressing the technical hurdles of long-term automation. If we rely on robotics in factories to bootstrap colonies, we must ensure those systems can repair, adapt, and evolve. True autonomy means machines that can cope with dust, temperature swings, mechanical wear, and unexpected geology. Designing such systems is hard but within reach. Modern robotics is already good at repetition and controlled environments, and the next leaps are in machine learning, self-diagnosis, and modular repair. Imagine a robotic miner that can fabricate spare parts from ore and swap them in when something fails. That kind of modularity reduces the need for human intervention. Step 19 is thinking about adaptation of humans themselves. Over long timescales, humans living on different planets or habitats might change biologically, either through natural selection or intentional genetic modification. Lower gravity could mean taller, more fragile bones unless countered by exercise or augmentation. Different radiation levels might favor different DNA repair mechanisms. Societies might decide to genetically adapt for cold tolerance, better oxygen utilization, or resistance to particular pathogens. Those are messy ethical considerations. Who decides which changes are acceptable? But from a practical standpoint, a mix of environmental engineering, habitats, and biological adaptation, medicine and modification, will be part of making long-term life off Earth comfortable. Step 20 is the idea of seeding, rather than full colonization. Not every star system needs an entire city. Sometimes the best approach is to seed a system with infrastructure that allows future expansion when it's desired. That could mean factories, energy collectors, storage depots, and a small maintenance crew, enough to support future waves of settlers. This is efficient because you don't have to commit to full colonization all at once. A seeded system can quietly become an economic node in a network that only later transforms into a population center. Step 21 involves the political choices about who gets to expand and why. Historically, expansion on Earth was often tied to state power, corporations, or religious enterprises. In space, governments, private companies, and international consortia will likely all have roles. Private enterprise may lead in early mining and tourism, while scientific exploration is often publicly funded. Over time, ownership and jurisdiction of off-world resources become hot topics. International agreements like the Outer Space Treaty provide some ground rules today, but they'll need updating as settlements grow. That's both a legal and a moral conversation. Who owns an asteroid, a moon, or a man-made habitat? How do we ensure fair access and prevent exploitation? Step 22 is integrating new technologies that change the rules entirely. Nanotechnology, if realized at a mature level, could revolutionize manufacturing. Tiny machines that rearrange matter at molecular scales could greatly reduce the need for large factories and heavy equipment. Similarly, breakthroughs in energy production, practical, safe fusion or novel antimatter handling, could free colonies from energy scarcity. Even incremental improvements in AI and robotics change the cost dynamics of expansion. The important thing is that the path to the stars is not a single technological bottleneck. It's a chain of many improvements, and progress in one area changes what's feasible in another. Step 23 is dealing with unknowns. The galaxy might host environments we don't expect. Planets with odd chemistry, unexpected radiation belts, or life that's very different. That's why scouts and probes are crucial from the beginning. They send back spectroscopic readings, surface scans, and environmental data that help planners decide where to build. An exploratory approach, send probes, study, then send infrastructure, reduces the risk of catastrophic mistakes. Step 24 is the cultural imagination that sustains long projects. Building across centuries requires narratives that motivate people beyond a single political term or lifetime. Some motivations are obvious: scientific curiosity, the drive to survive as a species, economic gain. Others are cultural or spiritual, the desire for freedom, new starts, or to become a multi-world species. Historically, the grand projects that lasted generations had narratives, cathedrals, railroads, or space agencies, and new galactic-scale projects will need similarly inspiring goals to maintain funding and public interest. Step 25 is considering the potential for contact. If we ever do encounter an independent technological civilization, the situation becomes far more complex. Contact scenarios range from profitable trade and knowledge exchange, to conflict, to mutual avoidance. A rational expansion plan should include strategies for detection, cautious approach, and non-destructive interaction. Interstellar laws or protocols might evolve, but given the communication delays, any meaningful interaction will require thoughtful, long-term diplomacy. Step 26 is balancing exploration with preservation. The urge to spread can conflict with the value of preserving natural systems. Many scientists argue for protecting ecosystems we find, both for their intrinsic value and because they might hold clues to life's origins. Ethical colonization strategies might prioritize sterile systems, build low-impact habitats, or set strict rules on how to interact with biospheres. That's an ongoing moral conversation for which there are no simple answers, but it needs to be part of planning. Step 27 is how human identity changes. Over generations, people born in different gravitational environments, with different technologies, and different cultural legacies will ask new questions about what it means to be human. Are uploaded minds still human? Are long-lived biosynthetic beings part of the same family? These identity changes will be gradual and messy, and they'll shape politics, law, and daily life in ways we can't fully predict. Step 28 is contingency planning for the truly unexpected. Astrophysical hazards, like gamma-ray bursts or nearby supernovae, could pose existential threats to localized regions. Building redundancy across many systems reduces that risk. Also, tech risks, like self-replicating machinery going awry, must be anticipated with robust controls. Research into safe design and international norms for new technologies should accompany any colonization effort. Step 29 is maintenance and culture of knowledge. Knowledge decays if not actively preserved. Libraries, digital repositories, and cultural institutions must be established on multiple independent nodes. The loss of a key knowledge site on Earth might be devastating if no copies exist elsewhere. Regular backups, distributed archives, and robust education systems in every colony ensure the continuity of science and technology. Step 30 is acceptance of timeframes. Humanity has projects that last centuries already: cathedrals, universities, and even some scientific observatories. Colonization across the galaxy is likely a multi-generational effort. That requires a social contract in which people accept that their work helps future generations thrive in ways they may never see firsthand. That's different from our modern short-term incentive structures and demands thinking in terms of stewardship and legacy. Bringing all these steps together gives a clearer picture. The route to a galaxy full of human, or human-originated, settlements is incremental, technical, ethical, and social. It starts with making Earth into a reliable launch pad and builds through a system of local resource use, automated factories, and carefully staged missions. It involves choosing when to send humans and when to send machines, how to deal with the laws and ethics of new worlds, and how to build economic and cultural systems that can operate with centuries-long delays. Each star system conquered or settled becomes a node that can either send out more seeds or become an endpoint in its own right. Over geological timescales, a civilization that maintains a steady outward push can make the Milky Way a web of habitats and industrial nodes. The exact form that civilization takes, whether biological, cybernetic, or a hybrid, will depend on choices made at each stage. We may see compact digital colonies buzzing with uploaded minds in artificial habitats, alongside agricultural worlds where people farm under domes or within engineered ecosystems. We may see outposts that specialize in energy collection, others in manufacturing, and still others in pure research. This is not a certainty, and it's not inevitable. Many things could stop or alter the process. Technological dead ends, economic collapse, political decisions to prioritize earthbound goals, or ethical constraints that prevent certain kinds of expansion. But when you lay out the steps, build an off-world economy, master ISRU and automation, develop reliable interstellar propulsion, seed systems with self-replicating factories or cautious human missions, and then scale energy capture and culture, you get a practical roadmap that shows colonizing the galaxy is more a problem of time, coordination, and will than a single impossible leap. Think of it in human terms. The age of exploration on Earth didn't start with one ocean-crossing ship that could build an empire on its own. It started with navigational advances, better ships, small settlements, supply chains, and decades of hard work. Over generations, networks of trade and control spread across continents. The galaxy is the same story writ vastly larger, a sequence of technological improvements, economic incentives, social institutions, and ethical choices that together determine whether and how humanity spreads. Now let's get into a few specific examples that make these steps feel concrete. Imagine a robotic seed factory the size of a shipping container. It's launched to a near-Earth asteroid and breaks off pieces of rock to build a small refinery. Over a few decades, using solar power, it manufactures more containers, welding them together into a larger processing plant. Within a century, that initial site produces metal beams, solar panels, and a few thousand tons of raw material. Those are used to build an orbital habitat, some propellant depots, and a small fleet of probes. One probe heads to Alpha Centauri carrying the blueprints for more of the same. It takes a few thousand years to get there at modest speed, but upon arrival it finds a small moon with enough ice and rock. The probe lands, builds a similar seed factory, and the process repeats. Over a few 100,000 years, that expanding network could reach across much of the local spiral arm. Another concrete example, a light sail swarm built in orbit around Earth. Thousands of small, cheap probes are launched by a laser array. Each probe is a few grams. It carries sensors, transmission gear, and a tiny amount of advanced material for data storage. The laser accelerates the probes to 20% light speed and mass, sending them toward our nearest stellar neighbors. Some will fail. Some will arrive in about 20 years. The successful ones collect data, send it home over centuries, and help chart good targets for the next generation of interstellar missions. This is a reconnaissance-first approach. Get knowledge before committing humans. Finally, imagine orbital cities built from asteroid materials around red dwarf stars. Red dwarfs are smaller and longer-lived than our Sun, offering stable energy for tens or hundreds of billions of years. They flare, which is a hazard, but shielding and orbital positioning can mitigate that. A red dwarf's long life makes it an appealing place to build long-term habitats that will endure for far longer than Earth's habitable lifetime. A network of habitats around many red dwarfs could be a resilient backbone for humanity's expansion, even if individual planets are not truly Earth-like. All these steps and examples point to the same core idea. Expansion is a chain of manageable innovations, each solving part of the problem. Scale, timescales, and ethics are the big variables. The human species has both the curiosity and some of the tools needed to start the process. What's uncertain is whether we organize the political and economic will to sustain it, whether we develop the right technologies in time, and how we choose to interact with whatever we find. So far we've looked at the technical and social steps. The next natural area to explore is comparison of timescales and numbers that give a feel for how fast this expansion could be and what it would cost in energy and materials. We'll go into that next, calculating realistic speeds for probes and ships, and looking at how replication times and hop distances change the overall timeline for filling the galaxy. We'll also consider how different strategies, fast small probes versus slow heavy ships, biological settlers versus digital minds, affect the character of the expansion and the kinds of civilizations that might emerge. All right, let's get concrete. If we want to talk about colonizing the whole Milky Way, numbers and timescales are where the abstract idea becomes real. How fast can we get from star to star? How much energy does that cost? How quickly could a spreading civilization actually cover vast distances if it tried to? Answering those questions doesn't require futuristic hand-waving, just some honest arithmetic plus a few realistic assumptions. I'll keep it intuitive. Think of ships, travel times, and the time it takes to build the next ship once you land. First, speeds. Space is big, and the relevant unit is the speed of light, c. about 300,000 kilometers per second, or 1 light-year per year. That's an unsurpassable cosmic speed limit. Nothing can communicate faster than that. For travel, realistic proposals cluster at a few distinct regimes. Very slow, what our current chemical rockets and gravity assist tricks can do. They move at tens to hundreds of kilometers per second at best, speeds that would take tens of thousands of years to reach even the nearest star. Moderately fast, fractions of a percent of the speed of light. Think advanced fusion or nuclear propulsion concepts, or very long-duration ion drives. Speeds like 0.001 c to 0.01 c are plausible targets for multi-century or multi-millennia missions. Fast, a few percent to about 10–20% of c, that's where beamed propulsion, powerful lasers pushing sails, or very advanced fusion designs sit on paper. Reaching 0.1 c, 10% of light speed, would get you to Alpha Centauri in about 44 years. Extremely fast, close to light speed, these are the toughest because relativistic effects and immense energies come into play. For now, most practical discussions focus on the first three categories. Travel time is simple arithmetic. Distance divided by speed. Alpha Centauri, our nearest stellar neighbor, sits 4.37 light-years away. At 0.1 c, that's roughly 44 years in transit. At 0.01 c, it's about 437 years. At 0.001 c, it's 4370 years. Scale that out across more distant stars and the difference becomes massive. But travel time is only part of the picture. Suppose you land at a target system, you don't just snap your fingers and launch the next ship. You have to set up a factory, mine local resources, turn them into parts, assemble a spacecraft, and fuel it, unless you used beamed propulsion. That local setup, call it the replication or bootstrap time, could range from a few decades to several centuries or longer, depending on how advanced and modular your seed equipment is. This is the crucial factor that turns single-ship travel into colony networks. A simple model ties these pieces together. Pick a typical hop distance L, how far between useful stars, an interstellar ship speed v ship, and a setup time t setup. The time between when one colony is established and when it launches the next colony into the next hop is roughly t total equals t setup plus L/v ship. The effective speed of the colonization front, that is, how fast the edge of the colonized region moves outward, is about v front equals L/t total. That's intuitive. You go L every t total years. Plug some numbers in and you get eye-opening results. Take L equals 5 light-years, a reasonable average spacing if you pick out good candidate stars. V ship equals 0.01 c, a fast but credible non-relativistic speed. And T setup equals 100 years, an optimistic but plausible modular replication time. Travel time is 5/0.01 equals 500 years, so T total approximately 600 years. That gives V front equals 5/600 approximately 0.0083 light-years per year, or about 0.83% of light speed. At that front speed, crossing the galaxy, about 100,000 light-years across, would take on the order of 12 million years. That's long compared to human history, but tiny compared to the age of the galaxy, about 10 billion years. If you slow the ship to 0.001 c, and hold setup time the same, T total becomes 5,000 plus 100 equals 510 years, and V front approximately 0.00098 c. Crossing 100,000 light-years then takes roughly 100 million years. Change T setup to 1,000 years and it grows more. Faster ships, shorter setup times, and shorter hops all speed the wave front. You can also swing the relationship the other way. If your ships are tiny, fast probes, like laser-driven gram-scale sails, they may reach 0.2 c or more and cross to nearby stars in decades, but they can't carry big factories. So they'll be excellent scouts. A reconnaissance-first approach uses fast, cheap probes to map systems, find resource-rich bodies, and maybe deploy tiny infrastructure, then send heavier, slower seed ships when you know where to invest. That's close to the breakthrough Starshot idea scaled up. Now let's talk about the energy cost. Accelerating mass to a given fraction of the speed of light takes a lot of energy. For non-relativistic speeds, we can use the familiar kinetic energy formula, a half mv2. A useful reference point. Accelerating 1 kilogram to 0.01 c requires about 4.5 times 1012 joules. Expressed another way, that's about 1.1 kilotons of TNT equivalent. Push that same kilogram to 0.1 c, and the energy jumps to roughly 4.5 times 1014 joules, about 110 kilotons of TNT equivalent. The jump is quadratic. 0.1 c is 10 times the speed, so the kinetic energy scales by 100. Those comparisons help. If you're accelerating a few grams to high fractions of c, a laser sail probe, you need big but manageable pulses of energy. The breakthrough proposals talk about 100 gigawatt-class laser arrays pushing tiny sails for minutes. But once your payloads weigh tons, the power and total energy necessary become enormous. And there's another key point. Chemical rockets are hopeless for interstellar speeds. They simply can't carry the fuel needed without absurd mass ratios. That's why concepts that avoid carrying large fuel loads, beamed propulsion, fusion propulsion, or even using local propellant like water from comets, are so attractive. There's also an important practical cost: shielding. At appreciable speeds, interstellar dust and gas endangered spacecraft because even tiny particles pack enormous kinetic punch. Imagine striking a grain of sand at 10% of c. The energy release at impact is comparable to a high explosive blast on a microscopic scale. For small-scale, cheap probes, you can accept some losses. You send thousands, expect many to fail. For a huge human-carrying ship, that's unacceptable. That implies heavy shielding, redundancy, and repair capability, and shielding adds mass, which then requires more energy to accelerate. It's a vicious cycle that pushes manned interstellar missions into the realm of huge engineering projects unless you accept slow speeds. With these constraints, strategies start to look clearer and different approaches emerge, each with trade-offs. Strategy 1, slow but massive, the slow boat approach. These are heavy, self-contained generation ships or ships that carry everything needed for a colony on arrival. They travel at modest speeds, perhaps 0.001 c or less, and rely on biological continuity or multi-generational crews to maintain civilization en route. They're expensive and slow, but conceptually simple, take humans and infrastructure along. The cost per person is enormous because you're hauling mass for long distances. Strategy 2. Seed factories and von Neumann-inspired replication. Here you send robotic units that are designed to use local materials to build infrastructure, refineries, factories, habitats, and new copies of themselves. The advantage is dramatic. You don't carry all the mass you need. The drawback is complexity and risk. The machines must be able to operate in unknown geology and climates, manage repairs, and adapt. If this can be done, the number of nodes can grow quickly. The mathematical ideal of exponential growth, each node building 2, then 4, then 8, sounds irresistible, but it's constrained by travel time and the finite number of neighboring systems reachable in a given time. In practice, you get something like an expanding wave front rather than perfect exponential growth. Strategy 3. Fast, cheap scouting followed by slow colonization. Laser sails and tiny probes race out to scan systems, sending back data over centuries. That information highlights promising targets where you later send seed factories or human missions. This staged approach minimizes early investment in heavy propulsion and reduces risk because you don't commit to settling a poor system. The downside: information still takes years or centuries to arrive, so planning is slow. Strategy 4. Digital expansion, sending minds instead of bodies. If uploading or emulating human-level minds ever becomes feasible and ethically acceptable, the mass and energy costs of sending a person drop dramatically. A digital mind could be encoded in megabytes to gigabytes of data and run on computational hardware that can be made small and robust. That hardware could, in principle, be manufactured on-site by seed factories. Digital minds tolerate radiation and cold in ways biological bodies don't, and can be copied easily. This changes the economics of expansion. A civilization that primarily spreads as software could produce enormous numbers of observers per unit of mass and energy. The ethical and identity issues are profound, but the raw mechanics of expansion become much easier. It's useful to see some concrete scenario math to compare timescales. Start with a single colony and some simple rules. Each colony can, given t total years, send out one colony to the next system at distance L. If every colony does this in parallel, the number of colonies grows like the volume of a sphere swept outward by the front. But if every colony instead builds multiple outward explorers, you get faster growth. A crude but revealing calculation is to consider how many hops you need to reach a radius r, roughly r/L hops. If each hop takes t total years, the time to that radius is r/L times t total. Crossing the galaxy are 50,000 light-years to go from center to edge, or 100,000 across, results in the numbers earlier. Another helpful way to look at it is the doubling argument in social replication. Suppose each colony, once mature, launches a set of colonizers that increase the total number of colonies by a factor of b every t years. If b equals 2, doubling every t years, to reach n colonies requires t times log2 n years. The Milky Way has of order 1011 stars. Reaching even 1010 colonies, a tiny fraction would need about log2 1010, approximately 33 doublings. If each doubling took 500 years, that's only around 16,500 years. That seems shockingly fast, and that's exactly the point of the exponential logic. But exponential models break down when travel time is comparable to or longer than the setup time, and when resources or nearest neighbors limit growth. In interstellar expansion, the travel time becomes the bottleneck. You can't double faster than you can physically reach new stars. So when could humanity start to do any of this? We're already on the first steps. Reusable rockets, expanding orbital economy, plans for lunar and Martian bases, in situ resource use demonstrations, and steadily improving robotics. On the propulsion side, nuclear thermal and nuclear electric engines, beamed propulsion research, and fusion studies are all active to varying degrees. It's plausible that within a few centuries we'll have the technology to send practical robotic seed factories to near stars, even if human interstellar travel remains centuries away. That's critical. The first wave of interstellar expansion may well be robotic and autonomous. Energy and material scaling are often underappreciated. Building a Dyson swarm, a distributed set of solar collectors around a star to harness a significant fraction of its output, sounds fantastical but is straightforward in principle. Take an average star like the Sun with output 3.8 times 1026 watts. Even capturing a tiny fraction of that frees staggering resources. The trick is manufacturing at scale, which needs raw materials. Asteroids, small moons, and planetary crusts are the mines. The factories to turn ore into collectors will be numerous and robotic. Once you have huge amounts of energy and manufacturing capacity in one system, moving mass becomes easier inside that system, and you can launch many missions to neighboring systems, because the marginal energy cost per launch drops. So local energy capture and manufacturing are force multipliers for expansion. Let's talk about practical sizes for seed factories. Opinions vary wildly, but a hopeful baseline is that a modest, highly capable robotic seed factory could be on the order of tons, not millions of tons. Imagine a package: advanced robotics, modular 3D printers, energy collectors, and processing tools, engineered to land on an asteroid, and over a few decades, bootstrap a larger factory using solar power and the asteroid's ore. If those bootstrap factories can replicate and scale, a small initial investment becomes a big local industry. That's the same principle used in historical colonization. A few people establishing a port and mill can support many more. Scaling down costs and complexity is the engineering challenge. There are hard limits and risks to manage, though. One big risk is runaway behavior of self-replicating machines. If a von Neumann probe malfunctions or follows an unwise directive, it could consume resources indiscriminately and cause ecological or economic damage to local systems. Whether that's stripping an asteroid belt the local people depend on or fouling a planet. Designing robust constraints, ethical controls, and kill switches is essential. Another risk is the gray goo type fear in nanotech scenarios, where small self-replicators run amok. In practice, engineering controls and staged testing can reduce these risks, but they cannot be ignored. Radiation and health are another barrier to manned expansion. Cosmic rays and stellar flares are a constant danger. For humans in habitats, shielding matters. Thick layers of water, regolith, or specially engineered materials can protect occupants, but again, mass is the penalty. Building habitats inside asteroids, underground, or in well-shielded orbital structures helps. In systems with active flare stars, many small red dwarfs, careful placement, and extra shielding will be necessary if you want long-term biological life. Digital beings or robots don't require the same shielding investment, which is yet another argument for sending machines first. Social, economic, and political factors also shape the pace. In Earth's history, colonization expanded when there were both strong incentives, resources, trade, and the means to ensure profit or survival for the investing parties. Translating that to space, early motivations will likely be a mix of science, private profit, rare metals, helium-3 energy markets, and existential insurance, spreading humans for species survival. Government-funded science programs and international coalitions could provide the initial public goods like interplanetary infrastructure. Over time, private corporations may take on mining, manufacturing, and even habitat construction as technologies mature. The Fermi question creeps in here inescapably. If colonization can, under plausible assumptions, sweep across a galaxy in millions or tens of millions of years, and if other civilizations had a head start of even a few million years, why don't we see evidence of them? There are several categories of responses that people discuss. Maybe intelligent life is rare, Earth is unusually fortunate. Maybe civilizations tend not to expand across their galaxy because they self-destruct, lose interest, adopt inward-focused technologies, or decide not to spread for ethical reasons. Maybe they expand, but in ways that leave little detectable trace from our vantage point. For example, by staying small and distributed, by using stealthy technologies, or by converting mass to forms we don't recognize. Or maybe they're out there, and their observable signatures are subtle, and we simply haven't looked long enough or in the right ways. Each of those options is compatible with different colonization models. The possibility that we're alone in our region would make our future expansion an unusual responsibility, the first to seed life and technology across the stars. If humanity decides to pursue galactic colonization in earnest, the early priorities are fairly clear. Build a robust off-world industrial base, invest in advanced autonomous robotics, develop high-energy beamed propulsion and compact fusion, or equivalent, and advance our ability to detect life and suitable targets at a distance. In tandem, we'd need strong international agreements about the ethics of contact and planetary protection, plus safety protocols for autonomous machines. There are also clever accelerants to think about. One is the use of interstellar relay nodes. If you can place stations that act as refueling or recharging hubs in between systems, say, on resource-rich rogue objects or UIT cloud-like bodies, you reduce the amount of local manufacturing a new colony must do before it can launch its own interstellar hops. Another accelerant is harvesting stellar energy with swarms, which lets you build large infrastructure quickly and then dedicate excess energy to launching fleets. Yet another is focusing on long-lived stars. Red dwarfs outnumber sun-like stars and live far longer, making them attractive long-term investment targets despite their flare activity. Let's quantify a few illustrative futures to make the differences feel real. Conservative slow expansion. Start launching heavy seed ships at 0.001 C with T setup equals 1,000 years and L approximately 5 Li. Then each hop takes 5,000 plus 1,000 equals 6,000 years. Front speed approximately 0.00083 c, and crossing 100,000 Li takes 120 million years. That's slow on a human scale, but it's still less than the galaxy's age. Moderate expansion with automation. V-ship equals 0.01 c, T setup equals 100 years, L equals 5 Li. Travel plus setup equals 600 years, V front approximately 0.0083 c, crossing the galaxy in 12 million years. That's now a geological blink. Aggressive expansion with rapid replication. If you can push V-ship equals 0.1 c and T setup equals 10 years, this is optimistic. L equals 5 Li. Travel equals 50 years, T total equals 60 years, V front approximately 0.083 c. Crossing 100,000 Li would then take 1.2 million years. That's extremely fast in cosmic terms. Exponential local replication scenario. If local clusters of stars can be reached quickly, and each colony can produce several outward-bound craft in a few centuries, cluster-scale growth can look almost exponential for a while. That allows rapid occupation of local neighborhoods, even if expansion across the full galaxy remains limited by long-range hops. These scenarios highlight a core insight. Many reasonable parameter choices give colonization timescales much shorter than stellar lifetimes. The real barriers are not always physics alone, they're social, organizational, and ethical. Human will, resource allocation, and risk tolerance determine whether we adopt slow and safe approaches or aggressive replication. Another subtle but important constraint is the spatial arrangement of stars. The galaxy is not uniform. Some regions are packed with stars, dense clusters, others are sparse, the outskirts. Travel times depend on local stellar density. In dense regions, you can hop short distances fast. In voids, you need longer hops. That means expansion naturally starts faster in crowded regions and slows on the outskirts, an effect that shapes the shape of a civilization's spread. Practical engineering choices also influence the architecture of settlements. Instead of terraforming entire planets, in many scenarios, you'd build habitats engineered for comfort. Rotating wheels, underground habitats, or translucent domes. Those habitats are efficient. They provide controlled environments tailored to human needs, and they don't require changing planetary ecosystems on planetary scales. That makes many more star systems usable because you're not constrained to Earth-like surface conditions. One more thing worth noting. The costs and benefits shift over time. Early on, the biggest investments create infrastructure that lowers marginal costs later. Building a powerful laser array is hugely expensive, but once built it makes launching many probes cheap. Building robust space foundries and mining platforms is similar. In economic terms, this is a classic infrastructure investment with high fixed cost and low variable cost afterward. That's why nation-states or very large corporations are likely early drivers. Only actors with long-term horizons and deep pockets can afford the initial outlays. Throughout these conversations, it's tempting to treat colonization as inevitable if the technology exists. But reality is messy. Political will can collapse, priorities shift, ethical considerations change plans, and unforeseeable technological breakthroughs can create alternatives nobody predicted. The history of exploration on Earth is full of fits and starts. It took centuries for oceanic travel and colonization to reach a global scale, despite earlier knowledge and capability. Space may follow a similar pattern, with bursts of activity, plateaus, and new surges when enabling tech hits. Finally, there's an emotional and ethical dimension to this whole enterprise. Spreading life and intelligence across the galaxy could be seen as a grand insurance policy for our species, a celebration of curiosity, and a creative act. It could also be a way of changing environments irreversibly. That tension between expansion and preservation will likely shape policy. We will have to decide whether to prioritize protection of potential biospheres, the rights of newly created artificial intelligences, and the fair distribution of off-world resources among Earth's populations. All of these numerical and conceptual tools feed back into planning. If you were advising a civilization that wants to colonize responsibly, you'd push them to start with robust scouting capability, to invest in situ manufacturing, to favor options that let humans follow instead of sending humans as the first wave, and to create strong international rules for planetary protection and the use of autonomous self-replicating systems. You'd also emphasize redundancy, many independent nodes across different regions to avoid single-point failures. So, when people ask, how long would it take to colonize the galaxy, the honest answer is, it depends on the choices we make about propulsion, automation, replication, and ethics, and on how much effort and resources we commit. Under many realistic technical scenarios, the galaxy can be traversed and settled on timescales that are small compared with its age. Millions to tens of millions of years for wave-like scenarios, hundreds of thousands to millions if you push speeds and replication hard, and much longer if we favor cautious, slow, or entirely human-led approaches. The underlying physics, distances, speeds, and energy sets the framework. Inside that frame, social decisions determine the story we actually follow. If you wanted to move from "we could" to "we would," there's a gnarly middle layer of questions that matter. What would a galactic civilization actually look like from the outside? How would it behave internally? And what practical constraints would shape its choices? Those topics pull together physics, economics, sociology, and ethics. They also connect directly to why we've never clearly seen anyone else yet, the classic Fermi question, and they tell us something important about how humanity might behave if we ever decide to spread. Start with detectability. If another civilization had spread outward in substantial numbers, what signs would it leave that we could hope to spot from Earth? There are a few broad categories of observational footprints, what astronomers call technosignatures, that are worth keeping in mind because they're concrete and measurable. The most obvious is waste heat. Any powered civilization uses energy, and in most processes, converts a portion of that energy into waste heat that must be radiated away. If an advanced society builds huge energy collectors around a star, a Dyson swarm, and uses a non-negligible fraction of the star's output, the star's visible light would be partially intercepted and re-radiated as infrared. Astronomers can look for stars with strange infrared excesses that don't match natural explanations. We've done this with surveys like IRAS and WISE. The absence of many clear candidates suggests that if Dyson spheres exist, they're either rare, partial, or constructed in ways that don't produce easy-to-find infrared signatures. A second kind of signature arises from very deliberate transmissions, radio, optical lasers, or other narrowband signals beamed toward space. That's the traditional SETI territory. These are easy to detect if someone shouts loudly and directly at us, harder if they're quiet, directed at other targets, or use bandwidths we don't monitor. Then there are structural signatures. Regular occultations of stars caused by large artificial structures crossing in front of them, or periodic dips in brightness that don't match planets. Kepler and follow-up missions have flagged some odd light curves. Most turn out to be dust clouds, instrument artifacts, or strange but natural astrophysical phenomena. But in principle, a large engineering project around a star could be visible in transit data. Finally, a civilization that manipulates matter on large scales could change the composition of stellar or planetary systems. For example, mining an asteroid belt en masse could alter the infrared emission or the distribution of small bodies. Very advanced civilizations could also move entire planets or modify the spectra of their stars by dumping material into them. These are more speculative but theoretically visible across many light years. So why don't we see obvious evidence of galaxy-spanning civilizations? Several answers are possible and worth separating because each implies different things about our future choices. One possibility is straightforward. Intelligent, technological life is extremely rare. Another is that civilizations tend to self-limit, either because growth becomes unsustainable or because cultural or ethical choices lead them away from aggressive expansion. A third is that they do expand, but in ways that leave little detectable signature. For example, by living stealthily in low-energy modes, spreading as tiny automated probes that don't build gigantic structures, or existing mostly as software in efficiently cooled computation, centers that dump heat in ways hard for us to detect. A fourth is the timing answer. The galaxy is old, but civilizations may rise and fall on timescales that rarely overlap with our window of observation. Each of these options changes what we should prioritize if we decide to expand. That brings us to different archetypes of expansion, and the trade-offs they imply, not just technological trade-offs, but economic and cultural ones, too. One archetype is the energy-hungry, expansionist civilization that builds Dyson swarms and industrial harvesters on a stellar system scale. Its motivation is simple. More energy enables more computation, more manufacturing, and more population. This civilization would be relatively easy to detect if it uses a large fraction of many stars' outputs. Its footprint would be energetic and global. Another archetype is the efficient quiet civilization that aims to maximize computation and experience per unit of energy and mass. Such a group might intentionally minimize waste heat or radiate it in narrow spectral bands to avoid detection. Or it might migrate into black box-style structures where heat is radiated at very long wavelengths hard to detect against cosmic background. A third path is the machine-first colony model. Send swarms of small, highly efficient robots that harvest and build quietly, creating a distributed industrial web that looks very different from a handful of brightly engineered nodes. Each path has different engineering and ethical implications. Economics plays a surprisingly big role in all of this. On Earth, expansion historically required something worth trading or extracting. In space, raw materials, metals, volatiles, and energy are often the drivers. But what counts as valuable shifts when gravity wells, transport costs, and local abundance change the math? In the near term, asteroids containing rare metals would be valuable because hauling such metals out of Earth's deep gravity well is expensive. Later, when large-scale space manufacturing exists, energy and surface area for habitats could become the scarce commodities. That's why Dyson swarms look tempting to an expanding civilization. Harnessing a star's energy could power massive computation and manufacturing that outstrips anything you could do with planetary resources alone. Trade across interstellar distances, though, is tricky. The light speed limit and the energy cost of moving mass between stars mean that interstellar trade makes sense only for a narrow class of goods. Extremely high-value, low-mass items, rare isotopes, unique artifacts, or knowledge might be worth shipping across light years, but bulk raw materials probably aren't. That's why seed factories and local resource utilization are central to any plausible expansion. You produce what you need where it's needed, not by hauling it from home. Interstellar commerce might therefore focus more on information, design blueprints, migration of people or minds, and the exchange of cultural products that are cheap to transmit data but valuable to receive. Those choices feed directly into governance and institutional design. One major constraint of an interstellar polity is delay. Communication delays stretch from years to millennia depending on distance. That makes centralized control impractical. Imagine a central government trying to enforce policy on a colony whose messages take centuries to arrive. It's nearly impossible. The logical corollary is that interstellar expansion favors robust local autonomy, with local governments or corporations making most decisions. Over time, this autonomy leads to divergence. Legal systems, languages, social norms, and technologies evolve locally. Federated structures, voluntary leagues, or alliances of autonomous systems are plausible. They allow coordination on shared issues like planetary protection, trade protocols, or defense, while preserving local sovereignty. But that presumes strong cultural ties and incentives to cooperate across long time lags. Those are not guaranteed. Decision-making by non-human agents changes the picture further. If a large portion of expansion is carried out by AI or uploaded minds, the institutional forms could be radically different. Digital entities don't age biologically, can be copied, and can run at different subjective speeds. They can also be highly modular, clusters of minds tied together in networks or distributed across many machines. Governance among such entities could be algorithmic. Consensus protocols, reputation systems, and automated contracts might define most interactions. That could enable tight, rapid coordination even across light-lag distances if governance is encoded in robust, locally executing algorithms and legal smart contracts. But it also raises questions about identity and rights. A whole thrust of social philosophy gets dragged into engineering choices. Those philosophy questions are especially acute when it comes to planets that might host life. Suppose we find a planet with microbial life or even complex life. Should we colonize it? Many astronomers and planetary scientists favor strong protections. Microbial ecosystems, even if not intelligent by our standards, are part of the universe's natural experimentation with life and contain unique biochemistry and evolutionary history. If our value system includes preserving naturally evolved life, except in extreme circumstances, then the expansion policy should include strict no-go zones and prioritize terraforming of lifeless worlds or construction of orbital habitats instead. On the other hand, some argue that spreading life, even our own, has intrinsic value, and that seeding barren worlds with terrestrial organisms might be a moral good. That's a deeply contentious stance, and one that would require global debate before being acted on. In practical terms, this ethical division influences how much of the galaxy a civilization is willing to occupy or alter. The technical design of colonization systems interacts with these ethical choices. Robots optimized for mining and self-replication can be built with explicit constraints, built-in limits on resource consumption in certain regions, geofencing to avoid biospheres, or kill-switch protocols that require verification from multiple independent actors to disable. But the more autonomous and complex the machines, the greater the risk of unintended behavior. Designing self-replicating systems that are safe by construction is non-trivial. You need robust verification, secure firmware, and fail-safe principles that remain effective in environments you can't foresee. A conservative strategy is to maintain human oversight for critical decisions, at least until reliability is proven over many generations. The cost of that conservatism is slower expansion. The benefit is dramatically reduced catastrophic risk. Risk management in a galactic expansion program also has to account for rare but high-impact hazards. One class is astrophysical events. Supernovae, gamma-ray bursts, and close-passing massive objects could sterilize local regions. A prudent civilization spreads redundancy across many systems so that no single catastrophic event can wipe it out. Another class is technological. Runaway replication, artificial pathogen release, or destructive uses of concentrated energy, weapons, could threaten whole swaths of a civilization. Policies and technical designs that limit the ability of any single actor to deploy such technologies unilaterally reduce risk. That suggests a role for secure, international, or interspecies governance mechanisms. But again, enforcement across light years is a hard problem. Let's turn to the engineering architectures that enable expansion, because the architecture you choose strongly shapes strategy. One practical architecture is the star-hopping model with seed factories at each node. A seed factory needs to be compact yet capable. The essential capabilities are mining, smelting, basic chemistry, additive manufacturing at many scales, energy capture, solar arrays, possibly small fission reactors during shadowed phases, and robust robotics with modular repair. Designing such a kit that can bootstrap a larger industrial base on an asteroid or moon is a feasible engineering challenge at our current level of imagination. The useful mass of the seed factory might be in the tons range rather than kilotons, making launch to interstellar missions less absurdly expensive. Another architecture leverages beamed propulsion. A civilization builds high-power laser or microwave arrays that accelerate lightweight sails to high fractions of C with a big ground-based or orbital beamer. You can send thousands of gram-scale probes quickly and cheaply. Those probes are excellent for scouting and charting, and they can carry sensors to look for planets and biosignatures. This reconnaissance-first architecture postpones heavy investment in slow or heavy colonizing ships until you know where to invest. The downside is that beamed propulsion requires enormous upfront energy infrastructure. A different approach centers on moving habitats and entire construction elements, essentially producing a mobile industrial civilization that shifts mass where it's most needed. That can include mass drivers that launch raw materials from asteroids into transfer orbits, rendezvous and assembly in orbit, and then dispatch of large ships with fusion or nuclear pulse drives. These are logistically intense but conceptually continuous with industrial-scale projects we already undertake on Earth. The boost is that once you can manufacture large, complex structures in zero-G, building habitats and ships becomes far cheaper than hauling them out of deep gravity wells by rocket. A more speculative architecture is the computational expansion model. If computation is the civilization's primary goal, say, to create more conscious observers, then the aim is to maximize bits processed per watt and per mass. In that case, the civilization might build vast computing farms, cooled to very low temperatures, located in privileged positions like the outer reaches of systems where waste heat dissipation into cold space is efficient. The search signatures of such a civilization are different. Low visible output, significant cold infrared emission, and possibly localized alterations in small body populations used for raw materials. These architectures map to different timescales. Beamed sail scouts can be launched within decades of building the laser infrastructure. Seed factory hopping using fusion or nuclear propulsion might take centuries to reach maturity, but could then expand steadily. Machine-dominated expansion could accelerate once on-site manufacturing proves reliable, because machines can often reproduce faster than biological settlers can migrate and reproduce. We can also think about social incentives across those architectures. Early colonists might be motivated by scientific curiosity, ideology, or the desire for autonomy and new social orders. Companies might be motivated by profit, particularly early on when valuable materials on asteroids could be sold to Earth markets. Nations might fund infrastructure for prestige or survival reasons. Over time, as local economies mature, different incentives, long-term stability, cultural self-determination, the drive to propagate an ideology or biological line, take over. These incentives shape what gets built where. For example, profit-driven entities will focus on resource-rich systems and near-term returns, while cultural or religious groups might prioritize remote habitats offering social freedom. A practical and underappreciated issue is maintenance. On Earth, we take for granted the supply chains and social institutions that keep complex technologies running. Engineers, spare parts, training pipelines, and institutions that pass on knowledge. In a distributed galactic civilization, maintenance is local but knowledge must be preserved and retrained across generations. That implies educational institutions, robust documentation archives, and manufacturing standards so parts produced in System A fit systems in System B. Standards and interoperability become strategic assets. Whoever sets the standard early on can exert long-term influence by virtue of technological compatibility. This connects to the concept of locking technologies. If an early civilization establishes a widely adopted standard, say, a particular architecture for AI agents, manufacturing protocols, or data formats, it can shape the evolution of many downstream colonies. That can be beneficial. Standardization reduces friction and enhances cooperation, but it can also produce fragility. A flaw at the standard level can propagate widely. Therefore, designing robust, auditable, and modular standards becomes a governance priority. Another area where strategy matters is detection and contact. If we send probes to other stars, how should they behave upon encountering life or evidence of intelligence? If probes are purely scientific, they might observe and transmit without interfering. If they're designed to seed or build, the stakes are different. Many ethicists propose cautious rules. Verify, avoid irreversible action, and only proceed with clearly defined and broad consent. But consent is tricky when dealing with wholly separate ecosystems or unknown intelligences. The contact protocols humanity might adopt will matter. They could range from a strict non-interference stance to a more interventionist approach that prioritizes spreading human-related life. Designing protocols that can be embedded in autonomous machines, so they don't take drastic actions on their own, is a practical engineering challenge with moral weight. Let's make this more concrete with a thought experiment that combines many of these ideas. Imagine an international consortium builds a laser array and begins launching gram-scale sail probes to nearby stars. Over 50 years, tens of thousands are sent. Many fail, some arrive and map promising systems, and a handful detect planets with resources and possibly signs of life. The consortium then decides to send heavier seed factories to a system that looks lifeless but resource-rich. The seed factories land on a dry moon, begin mining, and over a century produce more substantial infrastructure, including habitats that attract the first human wave. A few colonies choose a conservative path, building habitats in orbit and mining asteroids for raw materials. Others select surface settlements on easier-to-adapt worlds. Over centuries, these nodes become semi-autonomous. They trade information and culture, and occasionally exchange people or data. Meanwhile, a separate faction within human civilization chooses to invest in uploading and AI, launching purely digital colonies optimized for computation. Those digital colonies expand rapidly within the constraints of energy capture and create a dense web of computation centers around many stars, but they radiate waste heat in ways that are hard to detect from Earth. Centuries later, when astronomers on Earth look for megastructures, the signatures are patchy. Some systems show clear industrial footprints, others look normal. That mixed outcome would be consistent with the kind of clean but messy reality we might expect. We can connect these scenarios back to the Fermi question. If expansion can be done, why the silence? One persuasive answer is that expansion yields many possible equilibria, and some of them are quiet. A civilization that achieves efficiency and prudence can spread mainly as software and small machines, minimizing grand megastructures and leaving subtle footprints. Alternatively, some civilizations might collapse or choose not to expand for ethical reasons. The point is that absence of evidence is not evidence of absence. It's an observational constraint that needs careful interpretation. A last practical issue worth exploring is transition management. If humanity decides to take the first steps, how should we sequence investments to reduce risk while maximizing future options? A reasonable agenda includes: 1. Build a reliable off-world industrial base with redundancy and strong safety governance. 2. Accelerate robotics, autonomous manufacturing, and ISRU while developing rigorous standards and auditability. 3. Invest in scouting technologies, beamed probes and improved telescopes, to map targets and look for biosignatures. 4. Fund ethical and legal frameworks for interstellar behavior, including protocols for autonomous machines and planetary protection. And 5. Support research into propulsion options and robust shielding techniques. That portfolio hedges against mistakes. It improves near-term space capabilities, reduces dependence on Earth for critical goods, and buys time while we understand targets better. There's a practical cultural step here, too. Galactic colonization isn't a merely technological program. It's a long-term social project that requires narratives and institutions with horizons longer than electoral cycles or corporate quarterly reports. Encouraging and sustaining that kind of long-horizon thinking demands incentives, recognition, legal structures that protect long-term investments, and cultural education that values stewardship across centuries. That's the kind of change that has happened before. Look at universities, religious orders, or foundation endowments that endure for centuries. But scaling that mindset to planetary civilization is non-trivial. At the level of individual choice, people driving the early phases of expansion, engineers, policymakers, donors, will face decisions that have outsized impacts. They will have to decide which technologies to prioritize, how open to be with their methods, and how rigidly to enforce safety. Those choices are where ethical deliberation meets engineering constraints. Building self-replicating machines without careful international oversight would be reckless, deliberately restricting research risks, preventing beneficial advances. Balancing openness with protection is a policy problem that requires international cooperation and transparent, inclusive debates. The next set of practical questions to explore, and the logical continuation of all this, are numerical and comparative. How much energy and mass exactly would you need to sequester to build a meaningful industrial base around a star? What are realistic timelines for seed factories given current materials and robotics capabilities? How do different stellar neighborhoods in the galaxy, dense clusters, thin outskirts, or the galactic core, change the cost-benefit analysis for colonization? Those are quantifiable questions, and the answers will be shaped by the social choices we make about acceptable risk, ethical constraints, and investment levels. Exploring those numbers lets us move from speculative narrative to concrete roadmaps that planners and scientists could actually evaluate. So before we start launching the first interstellar hardware en masse, there's a lot of groundwork to do. Refine our observational searches so we better understand where life and resources are. Design safe, auditable autonomous systems that can operate with constrained oversight, and build governance that aligns incentives across diverse actors. The choices made now about who gets to decide, how transparent processes are, and how we value other biospheres will ripple outward across the stars as surely as any rocket exhaust. We left off with a clear practical to-do list. Get better at finding promising targets, build autonomous machines that can actually bootstrap industry off-world, and create governance rules that keep those machines and missions safe. Now let's dig into the numbers and engineering realities that make those ideas concrete. Because the difference between maybe someday and actually feasible often comes down to whether the math lines up. Start with the mass and energy budget for a plausible seed factory. What does a kit that arrives at an asteroid and turns rock into more machines actually need to carry? At a minimum, you want power generation, excavation and processing tools, modular fabrication systems, and some robotics. Think of it as a compact industrial workshop plus an inventor's toolkit. Solar panels, or a small radioisotope/fission power source for shadowed regions. Drills and grinders, chemical reactors for extracting useful elements, smelters or electrochemical furnaces, industrial 3D printers that can lay down metal and ceramic components, and a swarm of repairable robots that can do assembly and maintenance. Engineers working on these ideas often imagine initial packages on the order of a few tons. That sounds ambitious, but remember, you're not sending a whole factory in one piece. The initial seed contains flexible tools and master designs, templates and software that let it reassemble local materials into bigger structures. If it lands on a 100-meter class metallic rubble pile, the asteroid contains millions of tons of metal. The seed's job is to convert a tiny fraction of that into the next generation factory. So the heavy lifting isn't done by what you launch, it's done by what you can process on site. Energy matters a lot. For operations near a typical main sequence star, solar power is the natural first choice. If you can deploy modest solar collectors that provide a few kilowatts to tens of kilowatts continuously, that's enough to run electrolysis plants and small-scale additive manufacturing. Over years, continuous low-power work adds up. For faster bootstrapping in darker regions, beneath a thick regolith or in the outer system. You'll want either compact fission reactors or beamed power from a nearby collector. The key is that the seed factory needs a sustainable local energy source, otherwise it's simply a sophisticated tomb. Now the electronics problem. Modern civilization depends on highly refined microelectronics, silicon wafers, cleanrooms, and chemical precursors. Those are far from trivial to make in a primitive asteroid workshop. One approach is to accept lower performance but more robust electronics early on. Instead of attempting to fabricate state-of-the-art chips from the start, initial colonies can use redundancy and modular hardware made from simpler materials that are resilient to radiation, thermal cycling, and dust. Think of large, fault-tolerant computation modules assembled from many simpler processors rather than tiny high-performance nodes. Over time, as industrial complexity and cleanliness improve, you can work toward more advanced semiconductor fabrication. Another promising route is nanofabrication techniques that assemble devices differently, perhaps using directed assembly or additive processes that tolerate more surface contamination. Either way, the timeline for making modern microchips from scratch at an off-world site is long, but not infinite. That leads to a practical architecture, staged bootstrapping. The first seed plants are primitive but reliable. Power collectors, rock grinders, chemical extractors, and coarse 3D printers that can produce structural parts, gears, and simple motors. Once those are produced in bulk, the next stage builds better fabrication facilities, enclosed workshops with environmental control for higher precision work. Over decades to centuries, the facility matures from crude reproducer to full industrial foundry. It's the same layered approach we used on Earth: small workshops first, then mills, and finally complex factories. Time is the trade-off for mass and complexity. What about propulsion and the choice of targets? Not all stars are equal. Red dwarf stars are tempting because they're the most common type in the galaxy and they live for trillions of years, a reliability advantage if you're planning very long-term projects. But many red dwarfs are flare-active, throwing off bursts of energetic particles that can sterilize unshielded surfaces or strip thin atmospheres. If your goal is habitats where biological humans will live on the surface, that's a complication. However, if your plan mainly involves orbital habitats and machine factories, red dwarfs become very attractive. Their long, stable light output gives you a centuries to millennia-long energy source for modest orbital collectors. Sun-like stars are comfortable in the way our own is comfortable, habitable zones that allow Earth-like climates if a planet has an atmosphere and the right conditions. But they're rarer and have shorter lifespans than red dwarfs. Massive stars are bright and energetic, but their short lifetimes make them poor long-term investments. So a sensible early strategy is mixed. Scan broadly with fast probes and prioritize systems that are resource-rich, relatively quiet in stellar activity, and within reachable distances. Selecting targets is more than picking the closest star. You're looking for systems with accessible raw materials, asteroids and small moons that are easy to capture into working orbits, comets with water ice, and planets with useful volatiles. In practice, that means many potentially interesting systems are ones with belts of small bodies rather than just a single Earth-like planet. An asteroid belt clustered around a star can be a gold mine, literally in the sense of extractable metal, for building energy collectors, habitats, and later launch platforms. Communication and network architecture between nodes is a technical and social linchpin. Light-speed delays are the hard law. Messages between colonies take years or centuries depending on distance. That forces a store-and-forward model rather than real-time control. Practical networks will likely be built of relay beacons, expensive at first, but useful over time. Imagine a chain of laser relay stations or data caches placed at strategic locations. Each relay collects incoming packets, stores them, and then beams them onto the next node during scheduled transmission windows. It's like the old maritime system of way stations and ports for ships, but for light-speed packets. Design choices reduce human frustration. use predictable schedules and local autonomy. If a colony knows that a reply to a query from Earth will take 10 years, it will build decision-making culture that doesn't rely on that reply. Protocols and cultural norms will codify what can be decided locally versus what must wait for distant consensus. Think about email versus instant messaging. Some decisions animate asynchrony, others require synchronous coordination. Institutional structures will evolve to match the rhythm of interstellar communication. Security and trust are critical in such a system. How do you prevent a rogue node from sending bad commands to a remote seed factory? Cryptographic signing of command packets, multi-party verification, and resource passports are technical measures that can help. A resource passport is essentially a set of signed credentials that authorize a machine to extract and use defined quantities of material in given regions. A digital permit embedded in the fabric of the seed's firmware. Those credentials can be time-limited or require periodic renewals from multiple independent authorities. It's crucial to bake in safety. You don't want a single actor to switch a seed into full replication mode and consume everything in a system. That raises the danger of runaway replication. The classic thought experiment is the gray goo scenario in nanotech, but similar risks exist at larger scales. A self-replicating robotic fleet built without careful constraints could, if misdirected or maliciously altered, strip resources indiscriminately. Preventing that starts at design. Replication should require multiple redundant checks, offline human or quorum-based, authorization for large-scale changes, and physical or software kill switches that can halt replication if anomalies occur. On top of technical solutions, legal and institutional frameworks will be needed to prosecute or stop malicious actors. The governance problem is as important as the engineering one. Let's talk economics, because no large-scale project proceeds for long without incentives. Early on, commercial activity may focus on high-value, low-mass commodities. Rare metals like platinum group elements, used in catalysts and some high-tech applications, are a typical example. The logic is simple. It's often cheaper to find and process small amounts of rare materials off-world than to mine them on Earth at great environmental cost. Another early market is space-based manufacturing itself, producing components in microgravity that are difficult or expensive to make on Earth. Over time, as in-system manufacturing scales up, energy and industrial capabilities become the market. Large energy collectors and orbital habitats become exportable products or services. One can imagine a market for in-space bandwidth, manufacturing as a service, or even hosting environments for wealthy clients and specialized scientific labs. The cost curve matters. Launch costs per kilogram to orbit have plummeted with reusable rockets, and further declines from spaceplanes, orbital refueling, mass drivers, or even space elevators, if built, would accelerate off-world industrialization. A big fixed-cost project like a beamer or space foundry becomes economical when the volume of launches or operations is high. That's why nation-states or large consortia are likely to kick off the first big infrastructures, with private companies following to exploit niche markets. Risk and insurance markets will emerge too. Insurers will hedge the failure rates of seed deployments, and that will influence who bears upfront risks, where governments underwrite early development because the public good is big and diffuse. Private firms can then take on lower-risk, higher-payoff ventures. Detection of other civilizations is an observational complement to economic strategy. The search for technosignatures has matured beyond just listening for radio beacons. Astronomers now use infrared surveys to look for excess heat, photometry to detect unusual transits, spectroscopy to search for industrial gases in exoplanet atmospheres, and radio arrays to scan broad swaths of the sky at high sensitivity. Specific signatures that would raise eyebrows include large-scale mid-infrared emission from a star system inconsistent with natural processes, a proxy for large-scale energy use, narrowband laser-like signals, periodic dimming events that don't match planetary transits, and atmospheric chemical disequilibria that are unlikely to be purely natural. For instance, a mix of long-lived chlorofluorocarbons and oxygen. More exotic searches are also possible. A civilization focusing on computation might emit waste heat at very low temperatures to maximize computational efficiency, making detection challenging, but not impossible if we look in the right wavelengths. Or they might use neutrino beams, gravitational modulation, or other channels for communication that we seldom monitor. The observing game is partly one of breadth. The more different ways we look, the more likely we are to catch something we didn't expect. Turning back to engineering, let's examine some concrete timelines under different investment and tech scenarios. These are not predictions, but illustrative ranges to show how policy and technology change outcomes. Conservative development path. Over the next 150 years, the focus is near Earth. Industrial orbital facilities, lunar bases extracting ice and regolith, and Martian outposts with expanding ISRU. Within 300 years, expect robust interplanetary supply chains and automated factories in the outer solar system. Interstellar efforts would be limited to fast, low-mass probes for reconnaissance, and perhaps a few ambitious seed missions to the nearest stars at slow speeds, century-scale journeys. The bootstrap to active interstellar colonization in this path can take millennia. Accelerated automation path. Aggressive investment in robotics, modular seed factories, and a large beamed propulsion infrastructure could allow the first workable seed deployments to nearby stars within 200–400 years. These seeds might take centuries to fully bootstrap local industry, but by year 801,200 you could see viable off-world colonies in multiple systems in this scenario. The pivotal factors are reductions in launch costs, matured autonomous manufacturing, and durable governance regimes. Computational dominant path. If uploading and efficient computation become technologically and economically feasible, the cost of sending minds drops dramatically. Energy becomes the binding constraint rather than mass. A civilization that prioritizes digital expansion could construct large computing habitats around quiet stars and expand the computational footprint across many systems relatively quickly once energy capture scales. Timelines here depend heavily on breakthroughs in computation per watt and ways to minimize waste heat signatures. But expansion could be faster in subjective terms for those digital minds, because they can operate at accelerated subjective speeds relative to biological time. Each pathway carries different societal choices and trade-offs. The conservative path preserves human primacy in decision-making and prioritizes caution and planetary protection. The automation path leans heavily on machines and decentralized industry. The computational route questions whether biological continuity is the best route for expansion and opens deep questions about identity and rights. Now let's zero in on planetary protection and ethics again, because they shape which worlds we'll touch and how. The discovery of any life, even microbes, on another world creates a strong ethical imperative for caution. Many scientists argue that a planet with indigenous life should be off-limits to colonization unless the local biosphere is thoroughly studied and there is clear permission from an ethically representative body. That constraint is not trivial. If you decide to preserve all biospheres, your target set shrinks considerably and your expansion options change. It will push technology toward orbital habitats and mining of lifeless systems. Conversely, if a civilization chooses to seed life elsewhere deliberately, that's a powerful moral decision that will reverberate for eons. Those choices are not only philosophical. They will be encoded into policy and treaty law, because once machines and humans start moving, undoing damage is often impossible. Resilience planning deserves another pass. Redundancy is not just a technical habit, it's an existential one. If you want a species or a civilization to survive supernovae, pandemics, or political collapse, you build many independent nodes. That means diversification of technologies and a spread across different parts of the galaxy. It also means practical measures, multiple independent seed designs, distributed archives, biological samples, cultural records, and technical blueprints, stored in many systems, and staggered manufacturing centers so that no single failure wipes out a critical component. In effect, resilience is about not putting all your eggs in any one gravity well. A related, less discussed issue is cultural and educational continuity on long timescales. In an interstellar civilization, each colony will have to train technicians, maintainers, and scientists locally. Apprenticeship models and robust documentation will be core pillars. This means pushing for robust, durable educational systems that prioritize technical literacy and the specific skills needed for local maintenance. Imagine a small colony knowledge institute whose job is to rotate apprentices through every critical system so that knowledge isn't concentrated in a few elders. That's not glamorous, but it's fundamental. A colony with brilliant designs but no trained people to repair them is a fragile colony. We should also think about the local ecological impacts of off-world industry. Mining changes the orbits and surfaces of asteroids and small moons. Building massive solar collectors increases local shielding of stellar light. Even orbital habitats intercept a tiny fraction of sunlight that might otherwise hit a planet. On human timescales, the changes are small, but on geological scales they accumulate. Planning for minimal ecological disruption where life might exist, and even planning where it doesn't, will be a moral choice as well as an engineering constraint. Another element that shifts strategy is the heterogeneous structure of the galaxy. The galactic center is dense with stars and heavy elements, but also higher in radiation and dynamic chaos. The spiral arms are lively, with star formation and potential raw materials, while the outer halo is sparse. The practical upshot: expansion will progress unevenly. Dense regions allow short hops and rapid local growth. Sparse regions force long-range investments. A rational expansion strategy might focus first on seed clusters in denser neighborhoods to build competence and supply chains, then bridge to sparser regions as infrastructure allows. That uneven spread has interesting implications for detectability, too. If a civilization expands primarily in dense clusters, their signatures may concentrate in certain parts of the sky. That could be a reason we haven't noticed obvious signs. Maybe they're clustered away from us, or their footprints are in wavefronts that haven't yet reached our neighborhood. We've touched on many choices: engineering, ethical, economic, and political, and their interplay matters. One way to think about near-term policy is to adopt an options-preserving approach. Fund and encourage technologies that give us choices later without locking irreversible actions into place early on. Examples include funding reconnaissance missions before committing to heavy colonization of a system, investing in safe, auditable autonomous systems rather than black box replicators, and building international legal frameworks that require transparency and consent for large-scale actions. Those steps slow some forms of expansion, but they dramatically reduce risk and future regret. A concrete example might help make these ideas tangible. Picture a 5-stage mission plan for a nearby, lifeless but resource-rich star. One scout stage: a fleet of fast, low-mass sails is launched to the system to map bodies and gather spectral data. They return or beam data back over decades. 2. Assessment stage. Data indicates a set of small moons and an asteroid belt rich in water and metal. Ground-based and in-system telescopes refine orbital maps. 3. Seeder stage. A few compact, well-constrained seed factories are launched at moderate speeds. They are designed to be cautious. Replication requires signed multi-party approvals, and they carry explicit planetary protection rules. 4. Bootstrap stage. The seeds land on select asteroids and begin low-energy mining, producing structural elements and solar farms. Over decades, they assemble larger fabrication workshops under enclosed conditions. 5. Expansion stage. With stable local manufacturing and energy, the system sends out supplies and eventually new seeds to nearby systems. along with orbiting habitats for human settlers or digital habitats for uploaded minds. Each stage is gated by tests and transparency requirements. At each step, ethical committees review environmental data and legal bodies verify permissions. It's cautious, expensive, and slow, but it minimizes catastrophic mistakes. One last technical point worth exploring before moving on is shielding and collision risk for interstellar travel. You don't need relativistic speeds for this problem to be serious. Even at 1% of light speed, collisions with dust or small particles can erode or puncture hulls over centuries. Small probes can be sacrificial, send thousands, except that many will be destroyed. Large manned ships are a different challenge. Solutions include forward Whipple shields, layered sacrificial materials that vaporize incoming projectiles, and electromagnetic deflectors that use fields to push charged particles aside. Both add mass or energy demands. There's also the option of slow acceleration and deceleration profiles that keep peak relative velocities low, trading speed for safety. Again, the trade-offs are familiar. Speed versus cargo versus survivability. There's still a rich set of practical, numerical questions to explore next. How many megawatts of power does a seed need to hit various bootstrap timelines? How much mass per year can a matured seed system produce given available asteroidal resources? What are realistic failure rates for early autonomous systems, and how do those rates change the economics? Answering those questions requires modeling specific hardware, orbital mechanics, and social assumptions. The kinds of calculations engineers and planners do when designing real projects. They're the next step if we want to move from thought experiments to project proposals that a funding agency or consortium could evaluate. For now, the big picture is clear. The physical laws give us constraints and possibilities, but within them there's a wide space of viable strategies. The choices humanity, or any civilization, makes about risk tolerance, ethics, and investment will determine which paths get pursued. We can be cautious and human-centered, machine-first and rapid, or somewhere in between. Each path has different technical bottlenecks and different visible signatures to outside observers. And critically, these are not purely technical choices. They are social and political decisions with ethical weight that will shape the galaxy for eons. We've already seen that the physical laws give us a sandbox of possibilities. Distances, speeds, energies, and the hard limit of light speed shape what's technically doable. But the story doesn't end with rockets and robots. Once you accept that expansion across the stars is physically possible under a range of plausible assumptions, a whole new set of questions moves to center stage. What would a long-term, galaxy-spanning civilization actually build? How visible would it be to outsiders? How would it govern itself across years-long delays? And what responsibilities would it carry toward life that already exists out there? Those are the messy, human-sized questions that turn the engineering puzzle into a social and ethical one. Start with what a maturing interstellar civilization might look like at the system scale. Early phases emphasize local resource capture, mining asteroids, building orbital habitats, and assembling solar collectors. Later phases scale this up into truly enormous infrastructure. Millions of kilometers of light-catching hardware, vast manufacturing complexes, and dense networks of habitats. One popular concept for scalable human habitat is the rotating cylinder, the O'Neill cylinder. Make one with a radius of a few kilometers and a length of a few dozen kilometers, and you've created the equivalent of a small city with simulated gravity, controlled climate, and agricultural belts. A conservative engineering estimate suggests that a well-built cylinder, with efficient use of interior space, could house on the order of 100,000 to a few million people, depending on density and technology. That's not a planet, but multiply that by thousands or millions of habitats across many systems, and you get populations that rival planetary numbers without terraforming a single world. Energy is the currency of such an enterprise. For reference, A comfortable modern human lifestyle on Earth typically uses a few kilowatts of continuous power per person. Account electricity, transport, industry, and services, and you're in that ballpark. If an O'Neill habitat supports 1 million people at 2 kilowatts per person, that habitat needs about 2 gigawatts continuously, roughly the output of a small power plant. Building a civilization across many systems means amplifying that number by the number of habitats and factories you want. Which leads us to the Dyson idea. You don't necessarily need a solid shell. A Dyson swarm is a distributed cloud of collectors and habitats that intercept substantial fractions of a star's light. Harness a percent of a sun-like star's output, and you're talking in the range of 1024 watts, utterly enormous compared to planetary scales. That's why, in energy terms, stars are the logical next step once you can manufacture at system scale. The catch is scale and materials. Harvesting a meaningful fraction of a star's output requires an enormous area of collectors. At Earth orbit, the solar constant is about 1,360 W/m2. To harvest 1024, W would require about 7 times 1020 m2 of collector area, numbers that are hard to visualize because they dwarf planetary surfaces. Practically, you'd harvest from asteroids and small moons over centuries, building swarms piece by piece. The asteroid belt and Kuiper belt alone contain vast raw material. Converting that into orbiting solar collectors and habitats is the long-term industrial chore. Because the total mass required is large, the timeline to reach star-scale energy collection tends to be measured in centuries or millennia under sensible production rates. But the payoff, effectively unlimited energy relative to planetary standards, is game-changing. All of that raises the detectability question again. If civilizations build energy-hungry structures, they should radiate waste heat. Waste heat doesn't vanish. Thermodynamics insists it goes somewhere, usually into infrared radiation. That motivates searches for excess infrared emission around stars. Yet a civilization that intentionally minimizes waste heat or radiates it in ways that blend with natural backgrounds could remain hard to spot. A civilization of digital minds craving computational throughput might optimize by radiating heat at very long wavelengths, very cold emission, or by placing computational centers in environments where their waste is hard to detect. So even if many civilizations exist, their strategies could make them quiet. It's a simple, uncomfortable point. Detectability depends a lot on what choices civilizations make about efficiency and visibility. Visibility also depends on architecture. A civilization that spreads via giant seed factories that leave visible megastructures in many systems will be easier to spot than one that spreads as tiny, stealthy machines. The way you choose to expand becomes a signature. Sending heavy, manned colonists means you need big ships, large habitats, and robust supply chains, things that leave substantial footprints. Sending swarms of tiny robotic harvesters that reprocess local matter into more machinery is different. Those machines can be designed to be low emission and physically small compared to planetary scales. So our search strategies and expectations have to be broad. Look for waste heat, strange transits, unusual chemical signatures in atmospheres, and also for the subtle rearrangements of small body populations that indicate large-scale mining. Governance is another core issue. How do you coordinate societies separated by light years and centuries of communication delay? The simple answer is you don't, at least not centrally. Real political control across interstellar distances is impractical. The fastest way to make a colony resilient is to make it autonomous. That means that any interstellar polity will be a federation of independent nodes, bound together by agreements, trade, and cultural ties rather than direct command. History on Earth gives analogies. Colonial outposts often developed local institutions because central authorities were too slow or weak to micromanage. Expect a patchwork of political forms. Some colonies might keep strong ties to home, others will become fiercely independent, and some will reinvent social organization entirely. This political autonomy has implications for stability and conflict. If a colony is self-sufficient and independent by necessity, what's to stop it from adopting norms that diverge sharply from other colonies? In the long run, that divergence is inevitable. Language drift offers a simple illustration. Languages that begin to diverge can become unintelligible in a few centuries. If you put groups on different planets or habitats separated by generations, cultural and linguistic divergence accelerates. When political divergence occurs, conflict may follow, but the costs of interstellar warfare are huge. You can't easily project force across light years without enormous infrastructure and cost. Power projection becomes a matter of who controls energy and manufacture in their neighborhood, and who can deploy remote tools, e.g., autonomous systems or digital influence, effectively. That means diplomatic and economic tools will be as important as military ones. Think treaties, trade embargoes, and signaling via controlled technological disclosures. Economics underpins this entire system. On Earth, high-value, low-mass items like specialized electronics or rare isotopes can justify long-distance transport. In the galaxy, information becomes even more transportable. Design blueprints, cultural works, and software are lightweight and valuable. That shifts the nature of trade. You export ideas and designs, and you produce bulk materials locally. That economic partition shapes what gets shipped and what gets built locally. Interstellar trade is therefore likely to focus on knowledge, genetic material, special technologies, and people, or minds, rather than raw bauxite. If you accept that, it becomes clearer why seed factories and ISRU, in situ resource utilization, are central technical pillars. The economic logic favors sending compact, capable factories that can make heavy infrastructure locally. The engineering question is how to design such a seed. What mass, what modularity, and how much autonomy? Estimates vary, but a plausible initial target is a compact seed ranging from a few tons to a few tens of tons that can bootstrap larger factories given a century or two of local work. The seed should prioritize flexible manufacturing, steerable 3D printers, modular robots, power systems, solar array pieces, reserve batteries or compact reactors, and robust autonomy, diagnostics, redundancy, safe kill switches. Those are demanding but not absurd. The key is that you design for long-term stepwise scaling rather than instant industrialization. That architecture in turn changes how you think about risk. A self-replicating system is powerful but also dangerous. Imagine a robotic swarm designed to cut up asteroids into feedstock for new factories. Without rigorous constraints, a bug or malicious instruction could turn that capability into an ecological disaster within a local system. Strip mining that removes the very resources needed by other inhabitants or damages a planet inadvertently. Avoiding such catastrophic options requires both technical design controls and governance rules. On the technical side, restrict replication capacity, require multi-party authorization for major changes, and build robust authentication schemes. On the governance side, create treaties and enforcement mechanisms that control who can deploy such systems and under what conditions. Doing this at Earth scale is already hard. At interstellar scale, it becomes even more critical because remediation is slow and expensive. Life protection, planetary protection, is a particularly thorny and morally charged constraint. If we find a world with indigenous life, even microbial, we face a choice: preserve and study or modify and use. Many scientists advocate a precautionary principle. Don't contaminate worlds we find with life, because each independent biosphere is a unique experiment in biology. Ethics aside, the practical result of a strong planetary protection stance is that many potentially attractive resources will be off-limits unless they are clearly sterile. That pushes colonization strategies toward uninhabited small bodies, carefully sealed orbital facilities, and anthropogenic habitats rather than surface colonization of potentially living planets. In other words, ethics will shape engineering and economics in substantial ways. Now let's zoom out and look at how expansion patterns would sculpt the Milky Way over millions of years. There are different possible wavefront morphologies. One simple picture is the roughly spherical wave. Colonies send out expansion probes to neighboring systems uniformly, so the occupied region grows like an inflating bubble. But the galaxy isn't homogeneous. Stellar density, metallicity, how much heavy material a region contains, and the distribution of small bodies vary. Expansion in denser regions, like spiral arms, is easier because hop distances between resource-rich systems are smaller. In sparse regions, hops must be longer. The result is an uneven spread, rapid growth in dense clusters, slower trickle into voids. If a civilization's expansion strategy optimizes for low hop distance and quick bootstrapping, it will spread faster in crowded neighborhoods and lag in the outskirts. That patchiness could lead to what looks like a mosaic of settled pockets rather than a uniform civilization blanketing the galaxy. Another pattern is networked growth. If a civilization focuses on building interstellar relay nodes, permanent stations that serve as refueling or data hubs, expansion can take on a graph-like quality. Think of a supply chain through star systems. Secure a chain of nearby nodes, then use them to push further. Relay nodes reduce the amount of local manufacturing each new site must accomplish before it can launch the next hop, accelerating growth in that corridor. The downside is that relays are expensive and create strategic choke points that could be targeted or contested. There's also the computational route to expansion. If uploading becomes practical, and if a civilization's priorities shift to computation and subjective experience rather than biological life per se, the fundamental resource becomes energy, not raw mass. Such a civilization would optimize energy capture and heat disposal, arranging computation centers in thermodynamically favorable configurations. That could mean large, cold structures or carefully managed waste heat sinks. The footprint of such a civilization might be subtle at optical wavelengths, but pronounced at certain infrared wavelengths, or highly suppressed if they cool their waste heat effectively. From our observational standpoint, that makes detection hard unless we search in the right parts of the spectrum or look for indirect indicators like unusual small body depletion. Now let's turn to the human side. How would identity, culture, and social institutions evolve over long spreads of space and time? A few straightforward dynamics are worth noting. First, isolation accelerates divergence. A group cut off by distance and light time delay must be self-sufficient, which favors social traits geared toward local problem solving, conservatism in some domains, and innovation in others. Over generations, differences accumulate in law, language, ethics, and art. Second, environmental engineering and biological modification are likely to create further divergence. Low-gravity habitats, different diets, and possibly deliberate genetic engineering to suit local conditions will change bodies and preferences. Societies faced with long-term survival pressures may choose to tweak humans biologically to reduce resource needs, increase radiation resistance, or adapt to different day-night cycles. Those choices are sticky. Once a population adapts genetically or culturally to a niche, reversing it is hard. Third, the introduction of digital minds complicates the social picture. If minds can be copied, sped up, or run in different substrates, social structures can fragment along substrate lines. Biological humans might form communities with attachment to embodied experience and lifespan constraints. Uploaded minds could form high-speed networks that evolve quickly and develop goals orthogonal to biological concerns. That could lead to mutually beneficial relationships. Machines prepare environments for humans, humans provide values and creativity, or to tension over resources and influence. Governance questions about who has rights, how copies are treated, and how decisions are allocated become central. These are not merely science fiction dilemmas, they're design decisions with long-lived consequences. Maintenance and knowledge preservation are another theme. A tiny technical detail can become a civilization-level risk if no one knows how to repair it. On Earth, we have redundant supply chains and training programs. In an interstellar setting, a single colony might have to maintain entire classes of equipment with a small local team. This suggests a practical engineering norm: design systems for maintainability with low human skill requirements. Redundancy, standardized modular parts, and automated repair bots help. Knowledge preservation means robust archives, distributed libraries of blueprints, biological seed banks, cultural records, and repair manuals stored in many independent sites. That way, if one colony loses critical expertise, others can help over time through asynchronous transfers. Building those distributed insurance policies is part of responsible expansion. A final technical point worth spelling out is shielding and collision risk for interstellar travel, which we touched on earlier but merits a fuller look. Even tiny dust grains hit at tens of thousands of kilometers per second have huge relative kinetic energy. For large crewed ships, you need effective shielding, multi-layered Whipple shields, sacrificial debris layers, or long-range deflection fields. Those add mass, and more mass means more energy is needed to accelerate, which again raises costs. One mitigation is to accept slower travel with gradual acceleration. The energy per unit mass to reach a speed V scales with V2, so having speed reduces energy needs by a factor of 4. Slow ships last longer but are less time efficient. For robotic missions, you can accept high failure rates, send thousands of tiny probes, and accept that many won't survive. That's the practical difference between manned and unmanned expansion. Humans demand long-term survivability, which is expensive, whereas robotic colonists can be numerous and expendable. Those technical constraints interact with the ethics and governance we discussed. Suppose you find microbial life on a promising world. Do you preserve it at the cost of delaying expansion, or do you harvest resources and risk destroying an independent biosphere? That is a moral decision we'll face before we have a full interstellar infrastructure, and it will require international consensus if it's to be legitimate, which is why policy matters now. Investing in telescopes and reconnaissance probes helps. The more we know remotely, the better our ethical decisions can be informed. Developing international norms for planetary protection, protocols for autonomous machines, and legal frameworks for resource usage are all things we can do today to make expansion safer and more just later. In practice, pragmatic, options-preserving policies strike the best balance. That means building capacity without committing to irreversible actions prematurely. Examples: prioritize scouting and observation so decisions are data-driven. Design autonomous systems with built-in audit and consent mechanisms. Fund open international dialogues about the ethics of seeding life and AI rights, and create legal instruments that encourage safety and transparency. These measures don't halt progress. They slow down irreversible steps until we have enough information and social consensus to make wiser choices. If you step back, two broad lessons emerge that are surprisingly practical. First, the physics sets limits but not a single inevitability. Many technical paths are feasible, and which one is taken depends on social choices. Second, these choices are weighty because they echo for millennia. The way we design machines, allocate energy infrastructure, and decide on planetary protection will shape not just the next century, but potentially the fate of life in many systems. The combination of technical possibility and ethical responsibility makes the question: what if humanity colonized the entire galaxy? Less a prediction and more a planning problem. What kind of future do we want, and how do we build institutions and technologies that make it likely while minimizing catastrophic risk? Those are big questions, and they deserve public debate. They also demand practical work now. Better telescopes to map habitable and resource-rich systems, more investment in robust, auditable autonomy and modular manufacturing, stronger international legal scaffolding for space activities, and cultural institutions that encourage long-term thinking. The technical pieces, reusable launch vehicles, ISRU, advanced robotics, beamed propulsion, fusion research, all matter. So do the social pieces: education, diplomacy, law, and ethical foresight. There's no simple timetable for an event as immense as colonizing a galaxy. The range of plausible outcomes spans millennia to millions of years. But underpinning all the scenarios are choices we make now about research priorities, governance, and values. If we invest wisely in reconnaissance, safety, and diversified strategies, robots first in many cases, cautious protection of potential biospheres, and broad international cooperation, we make the long march outward both safer and more likely to align with values we can defend. If we neglect ethics and governance in favor of raw speed, we risk irreversible mistakes that could impoverish all future options. So the practical, grounded way to think about a galaxy full of humanity, or of our machines and digital descendants, is as an enormous coordination problem stretched across physics, engineering, economics, law, and ethics. Each technical advance gives us new possibilities. Each policy choice channels those possibilities into particular paths. The splendid thing about this problem, though, is that many parts of it are already within reach. Better telescopes, stronger international norms, improved robotics, and more resilient space industries. Those are the stepping stones. The rest is patience, prudence, and the willingness to treat the future not as a distant abstraction, but as a practical realm we help shape with choices made today.